Leah here from LeahForSci.com, and in this video we'll introduce the concept of chirality, looking at enantiomers, stereoisomers, chiral centers, and more. You can find this entire series along with my practice quiz and cheat sheet by visiting my website LeahForSci.com/chirality. Chirality falls under the topic of stereochemistry. Specifically, we're looking at stereoisomers. Don't forget that isomers are molecules with the same molecular formula, but something is different about them. Constitutional, rotational, conformational, different types of isomers. And the stereo portion tells you that you have the same molecular formula, same connectivity, meaning the order of atoms, but the difference is their specific orientation in space, meaning where they're locked into. Now this can include cis-trans isomers over a double bond or a ring, or stereoisomers, which I think of as chiral isomers, RNS. When I think of chirality, I think of handedness for the molecule. Many people are right-handed, some people are left-handed, and different tools and machines are meant to be operated with one hand or the other, the right or the left hand. Imagine taking one of those big, heavy, fancy gloves that's meant for your right hand and putting it onto your left hand. It just doesn't work. Right now we're looking at the top of my right and left hand, and they look about the same. I have thumbs in the same place, fingers in the same place, and when I turn it over, they still look the same. So while hands are the same though, notice that no matter how I turn them, imagine there's a mirror right here between them. Right now, my thumbs are mirrored, fingers are mirrored. There's still an imaginary mirror between them, still an imaginary mirror. No matter how I turn them, it appears that there's an imaginary mirror between them. But now what happens if I try to superimpose them? Well, my thumbs are sticking out, so if I turn it, now my fingers are in opposite direction. If I flip my hand so that my thumbs and fingers are aligned, well, my palms are in opposite direction. No matter what I do, there is no way for me to perfectly superimpose my right and left hand, making them mirror images to each other. So we agree that hands are mirror images to each other, and if these are your right and left hands, palm down on the table, they are the same, but they're mirror images of each other. And the only way that you can superimpose a hand would be if you took a thumb and added it to the other side, assuming the fingers were the same, took a thumb and added it to the other side. Now you see the right and left hand are exactly the same. In fact, there is a plane of symmetry going right down the middle, and that is the key. If there is symmetry, then your two hands will be superimposable, and they will not be unique. A right two-thumb glove will fit a left two-thumb hand, and the other way around. When thinking of chirality, we're typically looking at a chiral carbon. Every now and then you'll see a molecule that is chiral as a whole, or a nitrogen, for example, with 4 substituents and a positive charge. 99% of the time, it'll be a chiral carbon. A chiral carbon must have 4 unique substituents. If they're not unique, it's like having a two-thumb hand, and they'll be superimposable. In order to have 4 unique substituents, we're looking at 4 bonds to carbon, and that means it must be sp3 hybridized and tetrahedral in its shape. So for example, if I show you a carbon here, and I draw it in 3 dimensions so that I have 2 bonds in the plane of the page, one up, one down to the left, I have one coming out down, but out of the page, and one down and into the page. This is just one of the methods that you can use to draw a chiral molecule, but the key here is to recognize we have 4 substituents, and so they'll have to be unique. We'll show A, B, C, and D. I'm using these colors so that we can follow along with a model kit where the yellow represents the white. 4 unique substituents on an sp3 hybridized tetrahedral carbon gives me a chiral carbon in the center. This central or chiral carbon is referred to as the stereocenter, or the asymmetric carbon or asymmetric center. In organic chemistry, it helps to look and hold a 3D structure. If you don't have a kit yet, get one on Amazon by going through LeahForSci.com/kit, and if you purchase through my link, I do get a small commission. So notice here we have a central carbon atom with 4 unique substituents. This is considered the chiral or asymmetric center, and it's tetrahedral because it's sp3 hybridized. So notice that I have 2 apparently same looking structures where each one has a chiral center and the 4 same substituents. If you look at the 2 molecules, you can see an imaginary mirror between them because they are perfectly reflected in each other. And as I turn them, they are still perfectly reflected in each other. Since these are chiral with an sp3 central carbon and 4 unique substituents, because they have a mirror between them, they're considered enantiomers or mirror images. And no matter how I turn them, I can always find that mirror between them. But now if I try to superimpose them, let's see what happens. To place one on top of the other, I need these substituents to line up. So let's flip it and line up the red and the green. But look at what happened. The blue and white do not line up. If I try to switch it so the blue and white are lined up, then look what happened to the red and green. They don't match. Just like with my hands, something is sticking out. Remember, it was thumbs or fingers. Here, the only way to line up 2 of the substituents is to have the 2 other substituents be opposite. In fact, the only way I can superimpose these 2 is if I take some of the bonds and physically break them, moving the substituents around, just like the example of moving a thumb to the other side. And now, look what happens. The blue is lined up, white, green, and red, they are perfectly lined up. They're still chiral, but now they're 2 of the same chiral molecules rather than mirror images of each other. Let's prove it by trying to reflect them in each other. But look at that. The green and blue are reflected, but the red and white are opposite. They don't line up. If I try to put a mirror between the red and white, now the blue and green don't line up. So no matter what I do, I will not be able to show these as mirror images, because if they're chiral and they're the same, they're not enantiomers of each other, right? They're either the same or enantiomers. So we have the option for 2 different types of molecules when it's chiral. Going back to the hand example, if you have a right hand and a right hand, they're exactly the same. They'll fit the same glove. They'll be superimposable with each other. We're going to call them the same. If we have a left hand and a left hand, once again, they are considered the same. They are superimposable. Superimposable tells you that you can take one right hand and put it on top of the other right hand and it'll look exactly the same. Or take one chiral molecule and another molecule of the same chirality and put one on top of each other. They look exactly the same. There are 2 scenarios where you'll see a superimposable molecule. If you have 2 chiral molecules, but they're exactly the same, meaning they're not mirror images, they are considered superimposable. Or if you have an achiral molecule, a molecule that is not chiral because it has a plane of symmetry. For example, if you have a carbon with 3 rather than 4 unique substituents, for example, this central carbon has a methyl, a hydrogen, another hydrogen, and an OH hydroxy group. In this case, having 2 hydrogen atoms means this molecule has a plane of symmetry, and if it's not easy to see here, build it on your model kit and rotate it in this direction so you have the hydrogens on the right and left. We have 2 hydrogens coming out of the page, one to the right, one to the left. There's an OH going down and towards the back. There's a CH3 going straight up in the plane of the page, and look at that. Symmetry right down the middle. So if your molecules are chiral but the same, or if they're achiral with a plane of symmetry, they are going to be superimposable. Now let's see what happens if instead of 4 unique substituents, I have only 3. So we'll take off the green one and swap it for white. So let's start with creating mirror images. I have the red and blue. Red and blue. They are perfect mirror images of each other. But how is it possible to have mirror images if I can take the same molecule and superimpose it on the other one? How is a superimposable molecule also a mirror image? And the answer is 2 of the same substituents makes this molecule symmetrical. Notice there's a line of symmetry going right down the center. Again, a line of symmetry. No matter how I turn it, I can find that symmetry, and that makes this molecule achiral. Because this molecule has a tetrahedral sp3 carbon in the center, but 2 of the same substituent for a total of 3 unique, it's not chiral. And if it's not chiral, it doesn't have a mirror image. It's going to be superimposable on another molecule of its kind. And just because it's superimposable doesn't make them enantiomers, it just makes them superimposable because they're the same exact thing. If you have two molecules that are chiral, but they're opposite chirality, meaning right-handed and left-handed, then they are considered enantiomers. Enantiomers are chiral molecules that are non-superimposable because they're opposite to each other. And another common term you'll hear for this is mirror images, because one reflects into the other. In organic chemistry, we classify chiral carbons or chiral atoms as being R or S. In biochemistry and sometimes in organic chemistry when looking at organic molecules, you're going to use the DNL configurations, which tells you how it rotates plane polarized light. And while we're not going to discuss it in this series, just keep in mind R and S does not equal to D and L directly, because some R molecules will be D, some R will be L, and the other way around. So how do you tell if a molecule is R or S in organic chemistry? That's exactly what we're going to discuss in the next video. You can find this entire video series along with a chirality and stereochemistry practice quiz and cheat sheet by visiting my website leiaversailles.com/chirality. Are you struggling with organic chemistry? Are you looking for resources and information to guide you through the course and help you succeed? If so, then I have a deal for you. A free copy of my ebook, 10 Secrets to Acing Organic Chemistry. Use the link below or visit orgosecrets.com to grab your free copy. After downloading your free copy of my ebook, you'll begin receiving my exclusive email updates with cheat sheets, reaction guides, study tips, and so much more. You'll also be the first to know when I have a new video or live review coming up. If you enjoyed this video, please click the thumbs up and share it with your organic chemistry friends and classmates. I will be uploading many videos over the course of the semester, so if you haven't subscribed to my channel yet, do so right now to be sure that you don't miss out.